discussed. So what is the use of spectroscopy? So any unknown compound can be confirmed by two methods. One is chemical method and another one is the spectroscopic analytical method. Now chemical method so far you have used in BSc. You were given one unknown compound and then you are going through the prelim test and general test and functional group test and other test with melting point or boiling point, and based on that you are confirming the unknown functional group as well as the compound. So that is the chemical method. Another method is the analytical method, I mean the spectroscopic method. Now in chemical method, you are given at least 10 to 20 gram of the compound. But in spectroscopic method, it required only milligram or particles. And that particles are enough to identify the unknown compound. So you had seen the spectroscopic method like UV. So with UV visible, you will come to know the conjugation double bond. You will get an idea. With TLC, you will get an idea that whether the conversion has taken place and the product is formed or not. That's the TLC, the basic fundamental aspect. UV will indicate you the presence of the conjugation, alternative double bonds. Then comes to the IR. IR gives an idea about the presence of the functional groups in the unknown compound. And then comes the 1H NMR. So 1H NMR gives an idea about the proton hydrogen present in it and the nature and number of the protons. Whereas mass spectroscopy gives, or 13C NMR gives about the presence and type of the carbon, whereas the mass spectroscopy gives an idea about the mass of entire molecule. So by TLC, UV, IR, 1H NMR, 13C and mass, this 5, in that the mainly the 5 spectroscopy gives an idea about the unknown compound, structure of the unknown compounds. Because when naturally occurring compounds are very less quantity, it is difficult to carry out the chemical method. So in that condition, the analytical methods, that is the spectroscopy, is very, very much useful. So we will take it one by one. Before 1H NMR, I wanted to discuss the 13C NMR. 13C NMR. So you have seen that 1H NMR. And here we have written 13C NMR. So 1H and 13C, both are the isomers of the respective element. So normal is 12C. So 99% 12C, 12 carbon is available on the planet, which is having the quantum magnetic is I is equal to 1/2. So in that way, it is a 0, because in a shell, one is the both the spins remain anti-parallel, okay, in the shell. So one is the value of I is 1/2, and the NT is minus 1/2. So 1/2 is equal to 0. So 12C is not showing any kind of the intensity. That is why 12C is not showing and not used in the spectroscopy, because it required the intensity. So the isomer of 12C is required. Just hold. I can admit someone who are there. I don't know who are there. No. Nobody is there now. Okay, once again I wanted to share. Okay, so once again we are here. So so we were talking about the 13C. Okay, so the abundance of 13C is only 1%, and the abundance of 12C is 99%. So the quantum value of that I is equal to 0 in 12C, whereas in 13C it is 1/2. So that is why 13C is used up. In the same way, 1H NMR is the isotope of the NMR, is it, which contain only one proton. So when we are saying proton, so it does not have any electron. So electron is lost, and then the only thing is left, that is the proton. So in which electron is removed, it become proton. So that is why it is utilized as 1H proton, 1H NMR. So in 1H NMR, the value range of the delta ppm is 0 to 12 ppm, but the abundance of the carbon is more on the planet. That is why the range of this 13C is very high comparison to 1H NMR. And here you can see that the range of 13C NMR is 0 to 220. 0 to 220, whereas in 1H NMR it is 0 to 12. So here the type of carbon is given. In 13C we are just talking about the carbon that is present in the compound. So zero value is observed only when trimethylsilane, that is the standard, is taken, that is the trimethylsilane. So this indicates 0, and then rest of the carbon indicates the different values. So dear students, the range of this is very high, as I have mentioned, and here the chemical shift is given in the delta ppm. Now what is chemical shift? So chemical shift is the intensity that shows from zero to that particular intensity. So that is the distance. Okay. So here it is the RCH3. When you are saying RCH3 means it is the aliphatic hydrocarbon. So the range of this carbon atom is between 8 to 35. When the carbon atom is sandwiched by two other alkyl group, so it little bit increases. So it shows 15 to 50 range. When it comes tertiary, or you can say it is a CH, then it goes 20 to 60. Okay, 20 to 60. So, and when there is no proton is not present, then it goes 30 to 40. So with this range, you will come to know the type of the carbon. If the range is between 30 to 40, then it be quaternary. If it is 20 to 60, then it can be tertiary. 15 to 50, then it is the secondary, and 8 to 35, it is primary. Now it overlapping. If you look at this, 15 to 20, 20 to 60, 30 to 40, in between it is overlapping. That is why the advanced spectroscopy is also required in the 13C. But here we will come to know the idea about the carbon that is present in the unknown compound. Also, I wanted to say here, all these are the sp3 hybridized carbon atoms. Okay, sp3 hybridized carbon atoms. So in this case, you can say that the sp3 hybridized carbon can give the value between 8 to 60 maximum. Okay, now this is the sp3. Sorry, here it is the sp, it is triple bond. Okay, so the value of that is 65 to 85, whereas the sp2, that is double bond sp2, that gives the value between 100 to 150. But when it comes to aromatic, like a benzene carbon atom, so it always falls between 110 to 170. So this is the value of the carbon that is present in the aromatic ring, like benzene. So now if we talk about the 1H NMR, it comes around 6 to 8 ppm in the 1H NMR. But in carbon 13C, it comes to 1110 to 170. So the whole vast range of the carbon is there. It varies based on the substituents. When any other electronegative elements or atom is attached to the carbon atom, then definitely the de-shielding effect will impact based on the electronegativity of the atom, particular atom. So I minus is attached to the carbon, then it falls around 0 to 40. When Br is there, 25 to 65. Cl is there, 35 to 80. N is there, 40 to 60. And oxygen is there, 50 to 80. So this is due to the presence of the electronegative. So the de-shielding effect is impacting on it. Along with that, now you can see that all these are the carbonyl compound. So in many of the reference book, it is mentioned that the carbonyl group is very important, and it is very easy to identify the carbonyl group by the 13C NMR. So now you can see that here the carbonyl group of the amide. Okay, so it falls between 165 to 175. This is the carbonyl group of ester, correct? So it is 165 to 175. Both are same. It depends on the substituents. It varies little bit. Then this is the carbonyl group of what? It is the carboxylic acid. It is 175 to 185. We are talking about the value of the carbon, but carbon, the nature of the carbon is the carbonyl group. This is the aldehyde carbonyl group. So carbon of the carbonyl group of aldehyde. So it is 190 to 200. And finally, this is the ketone of the acetone like. Okay, acetone like ketone. So that value indicates the 205 to 220. Correct? So if you just look at these values, which indicates the different chemical shift in delta ppm. So highest delta ppm is of the carbonyl carbon of the carbonyl carbon, that is 205 to 220, and later the carbonyl carbon of the aldehyde, carbonyl carbon of the acid, carbonyl carbon of the ester, and carbonyl carbon of the amide. So this is what the range of the correlation of the carbon. Okay, it is hanged. So let me check out now once again. It is hanged. So let me share it once again. You can hold on for a few minutes. I am coming back because it is hanged. Okay, so once again I am back. So there is a range of the 13C is from 0 to 220. In one of the reference book, it is mentioned 0 to 240. Is it? So both can be considerable. Okay, so this is what we had discussed. Okay, now same thing is mentioned here with the values that is given. Okay, so this is the carbonyl carbon that goes towards it goes up to 220, whereas least is the hydrocarbons. That is also the aliphatic hydrocarbons. As I have mentioned, this is the range of the sp3 hybridized. This is the range of the sp2, and here it is the sp, that is the alkyne. And then here it is the C triple bond C, that is the alkyne, but in between, in the same range, there is a aromatic ring is present. This is the another chart for your, just for your knowledge. Okay, now one more thing I wanted to mention here, that this is the zero. Okay, this is the zero. So when you are going towards the left hand side, this is a LHS, correct? LHS left hand side show de-shielding effect, or also you can say that it is the downfield. It is the downfield. Whereas these towards the RHS, it is known as the upward field. Upward field. So RHS upward field, LHS downfield. So you can remember that de-shielding effect goes towards the de-shielding effect is goes towards de-shielding goes towards the downfield, whereas shielding effects goes towards the upward direction or right hand side, correct? So on your left hand side is the downfield, so 0 to it goes towards this. So in this direction, the de-shielding effect is increases, whereas at the right hand side, this towards this side, right hand side, the shielding effect can be increases. So de-shielding effect increase only when electronegative elements or any functional groups are attached, which is having any of the electronegative atom. Then it impacts on the de-shielding effect. Now you can see that based on that, this is very simple example that we have taken, that is the nitrobenzene. Okay, nitrobenzene. Now, if you are able to see what will be the value of NO2 will get, what will be the NO2 value will get? Hello? Are you there? Hello?
Yes, sir.
Okay, so do you have any idea what will be the value of NO2? So you will not get the value of NO2. We are talking about the 13C. So we will get the value of only this carbon atom. This carbon atom. Okay, this carbon atom. Rest of the, if we go for the value of NO2, then we have to go for the IR. From IR we will get an idea. But here just we are talking about the 13C. So we will get the value of the carbon. Now these two carbon atoms, I can number it 1, 2, 3, 4, 5, and 6. Okay, 6 carbon atoms are there. So carbon number 2 and 6 are same. So you will get only one peak. Okay, of course, when you can stretch it, you will get the overlapping, but by visualizing on the piece of paper, you will get only one peak because both the carbon atoms are same. Whereas carbon number 3 and carbon number 5 both are same. So you may get only one peak. And this is not equal. So you will get the different peak of this carbon atom and you will get the different peak of carbon number 1. So here, how many peak we can observe? How many peak we will get? This is the one of the peak. 2 and 6, one peak. 3 and 5, one peak. And fourth number is the another carbon atom, one peak. So total number of peaks we will observe, that is 4. Correct? Total number of peaks that observed are only 4. Getting everyone? Is it? So now here it is given. So now this is the electronegative functional group. So it goes towards the downfield. So this can be the peak of the very small, okay, carbon of this, where the NO2 group is attached. What is the name of this carbon atom? Carbon number 2 is known as ortho. Carbon number 6 is also ortho. Carbon number 5, 3 and 5 is meta. Whereas carbon number 4 is para. Correct? Now, do you know what is the name of this carbon atom? This carbon atom which is exactly attached to the NO2 group. Do you have any idea about this? The carbon.
Ipso.
Correct. Very good. Okay. It is ipso. Very good. So this is the ipso carbon atom. So the highest value of carbon is the ipso. Okay. It is a ipso. Correct. Then now it goes towards the upfield because NO2 group is attached to the carbon. Now both the carbon, nearer carbon are 2 and 6. So this is the value of the carbon atom of 2 and 6. Then this is the 3 and 5. This is the 3 and 5. Okay. And the final is the para carbon because it is very far from the NO2 group attached. Now in this also, if you are able to see, there is a black line. Okay, down black line, because two carbons are there, so it is overlapping. Okay, it is overlapping, but it is not clearly visible here. in by the instrument, but if you can go for the stretching, expansion of the graph, you will get that 2 carbon atom. Okay, 2. So this is how the carbon spectra can be looks like. So here, one thing I wanted to mention, that the 13C are very difficult than the 1H NMR, because 12C is not detectable, and it is 99% 12C is available in the earth. Another one is the magnetic resonance of the 13C is very weak. That is only 1%. So that is why it is difficult. It is also difficult because the range is very high. 13C range is 0 to 220, and it is mentioned that magnetically spectrum non-equivalent carbon gives the single unsplit peak. So you will not get exact idea about the number of carbon atoms, but you will get an idea that yes, carbon is there, because in previous example we have said that it is the equivalent proton, but minutely it was mentioned. Symmetry also renders splitting like C2C6 and C3C5, as we have mentioned in the previous example. This is very interesting in the 13C. So 13C 1H spectra, 13C 1H spectra split by the proton bonded directly to the carbon, directly to the carbon. So in this case, the 13C is hanging. Once again, it is the laptop is hanged. But here I wanted to say that the 13C 1H spectra is very useful, where the how may not only it gives an idea about the number of carbon atom present in it, but also gives an idea about the proton that is directly attached to the particular carbon atom. That is very useful. Okay. So just hold on, I can restart the laptop. So by the time, you can hold on for 30 seconds. Okay, I am back once again. Okay. So again, we have mentioned that the another example. So it is the graph of the same compound. It is the graph of the same compound. So this is the same compound. It is the same compound. Sorry. This is the compound. Okay, here it is also the same compound. The upper chain is not written. That is the only thing. So these are the graph of the two compound. So in the previous slide, the last point we have said that the 13C NMR gives an idea about the proton that is directly attached to the carbon is also mentioned. So here it is the graph of the proton coupled, correct? And this is the graph, second B graph is the proton decoupled. So what is the difference you can observe in the proton coupled graph and proton decoupled graph? So in proton coupled, there is a lots of noise. See this black line. This is the one thing. Whereas in this proton decoupled, the line is very clear. You can say in the spectroscopy, we can say that noise is very less. So noise is removed by the proton decoupled. Okay. Not only that, here so many peaks are observed. Correct? Comparison to that, only the high intensity peaks are only observed. And now you can clearly identify by this proton decoupled spectra. That spectra is B. That this is the CH3. Okay, here it is the CH3. Now in this case, it is little bit difficult to identify because here so many peaks are there. And why do this peak comes? Because the carbon coupled with the neighboring carbon also. Okay, carbon coupled with the neighboring carbon also. It is also coupled with the proton also. So both the things are there. That is why we are getting many peaks in the 13C. But to remove that noise, the proton decoupled, the another method is there. So that is the proton decoupled method. So here clearly mentioned. So you can just see in this region. Here there is 1, 2, 3, 4, 5, 6 peaks are there around. Whereas here only one peak is there. So that is hydrocarbon. So and it is towards the upfield. So definitely this is of the CH3. Okay. Now here you can say that there is a carbonyl carbon and carbonyl carbon of the ester. Okay. So that can be more than 150 the range according to that range. So here it is the carbonyl carbon. So it is somewhere 170 around. Okay, now another carbon is left, that is the CH2. Okay, so both the environment of the carbons are different. Here it is the COCH2 and that CH2 is attached to carbon. So that is why we are getting the value of this carbon, the carbon value of this carbon. Here it is the OCH2. Okay, so this carbon is directly attached to the oxygen. So that is why the value is towards the downfield, towards this carbon atom. See this difference in these two things. Okay, if you look at this, the carbon, here it is the carbon, this carbon that is attached to the another carbon and that carbon is attached to the carbonyl group. But here this carbon is directly attached to the oxygen. So that is why the value of this carbon is around 60 and the other carbon is around 41, 42. Okay. Now here it is the clearly mentioned, all the three graphs are mentioned. Now just look at this. The first graph is of the 1H NMR of this compound. Okay, so in which what will be observed? Only the proton. So 7 point, around 7.0, all the aromatic protons are observed. Okay, 1, 2, 3, 4, and 5 protons are there, but you can see that only singlet is visible. So if you expand it, you will get that splitting pattern. Okay, now here it is the you can say here it is the triplet. Here it is the triplet. So triplet, this this is the proton, this is the proton, correct? Now towards to that there is only there is a functional group attached, so this will give you only singlet, so that is the singlet, correct? Now CH2 is there, two protons are there, so this proton will follow the n plus 1 rule, n+1 rule. Okay, તો હિયર અહીંયા કેટલા છે પ્રોટોન? બે છે. તો આ જે પ્રોટોન છે કે શું બતાવશે? 2+1, so 2+1, so 3, so this is the triplet. So this is the triplet is of this, and here it is the 3. Okay, here it is the 3, but it will follow the n+1 rule. So 3 plus 1 is equal to 4. So it is a quadrate. So you can see that here it is the quadrate. So this is the quadrate of what? Quadrate of this. Okay, this is the triplet of what? This. Okay, because in 1H NMR it shows the value of the neighboring proton. Neighboring proton એટલે અહીંયા 2 છે. Okay, here it is 2, so this will show the triplet. Neighboring ma this will show the quadrate. Okay, so તમારે neighboring જે છે neighboring ને consider કરવાનું, પોતાનું નહીં. Is it? Here there is no neighboring proton available in this case, in this, so this will go for the triplet, even though there is a two protons are attached, because both the protons both the protons are surrounded by this functional group. This side there is no proton, so it will give you the singlet. Now this is the 13C NMR. Okay, 13C NMR. So 13C NMR, in this already we had seen the carbonyl carbon. This is the value of the carbon, this is the another value of the carbon, and this is the methyl group. But this is the graph between it is mentioned, that is the Okay. So from the above example, so whichever example we had seen that lots of noise was there and the coupling was there. So most of the 13C are surrounded by the 12C, which is having no not spin. So that is why they are not giving the spin coupling. And it is also difficult due to that the chemical shift range of carbon is 0 to 220. So that is why it is comparison to 1H NMR, it is difficult. Then here one thing is very precisely I wanted to say that directly bonded protons are strongly coupled with the particular carbon atom, and signal for each carbon is splitted directly bonded to H and followed the n+1 rule. So if the quadrate is there, I mean 3 protons are there, then you will get the quadrate. TMS in both the cases 1H NMR and in the 1H 13C it remains 0, and C2 C6 and C3 C5 because magnetically both the carbon atoms are same ortho position and meta, so that become the identical due to the symmetrical. Effect of substituent is not confined to only nearest nucleus as 1H. Now, to overcome from that issue, what is the issue in 13C? The carbon is coupled with the neighboring carbon also. The same carbon is also coupled with the directly proton. The same carbon atom is also coupled with the neighboring proton also. So due to that, lots of complexity is increases. So on the baseline of the 13C, you will see that zigzag lines. That is due to the cross couplings. So that is the one of the method is the broad band HD coupling. Broad band HD coupling. Okay. In short, it is known as BBD. Okay. So due to the BBD, 13C coupling is not observed. 13C is not observed due to the low natural abundance, or it can be removed. 13C is rare and peaks are very small, but you can say 13C 1H coupling is very strong, so complexity is increases. So 13C 1H coupling is removed by the BBD. So extra irradiation is given during the process such that it removes the 13C 1H coupling. So that noise can be decreased and you will get the clear peaks of the 13C of that particular carbon atom. Along with the C spectrum, uh, the irradiation of the band of the radio frequency that excite to all edge to remove. So that is why the 13C edge coupling can be removed. Okay. Another method is off resonance decoupling. Off resonance decoupling. So both the things, BBD and off resonance decoupling, both are the methods that is uh, familiar to identify the nature of the carbon. But when BBD is applied, all the unnecessary information is removed, but along with that, the necessary information is also removed by BBD. So to overcome from that, off resonance decoupling can be utilized. So here the molecule is given, that is the benzaldehyde, perithoxybenzaldehyde is given, where the value of the value is of given. But now just you can look at, this is the decoupled, you can say it is the BBD graph, whereas this is the off resonance decoupled spectrum. Okay, so now what do you observe, that in BBD so many things are removed, in BBD, but it can be regained, or lost data can be retained in the off resonance decoupled spectrum. So just we can take the example. Of course, the intensity of this is the one of the carbon atom in BBD, but the intensity of the carbon is given in off resonance decoupled is very high. Not only that, but here no splitting is observed, but here you can see the splitting is also there. So this is not only carbon atom. This is the carbon atom like C3, 5 or C2, C6 and C3, C5. Here also only singlet is observed in BBD, but in off resonance decoupled spectrum, doublet is observed. So it mentioned that two carbon atoms are present. Here is also more or less only one carbon atom, one singlet is observed, or very short peak is here. But in the off resonance decoupled spectrum, two splits, two peaks are observed. Here also it is almost only one peak is observed in BBD spectrum, but in off resonance decoupled spectrum, doublet is observed. So now you will see that what is the difference between the BBD and the ORD. You can say off resonance decoupling. Of course, BBD is good to identify the particular carbon, but it also removes all the 13C1H decoupling and it lost all the data. But that can be regained by the off resonance decoupling. So you will get the graph looks like this. So this is off resonance decoupling and the BBD. These two methods are there. So in off resonance, the multiplets becomes the narrow and not removed altogether and provide the particular information. So here, if you look at enough resonance, what do we give? There is no protons, only carbon atoms are there. So it will give you the singlet. There is only one proton, is there, so you will get the doublet by this carbon atom. If two protons are present, okay, so it will give you the triplet. Why? Because it follows the n+1 rule. So in carbon you cannot see the neighboring protons. You can see the directly attached proton. Here, directly attached proton. So this proton and these protons both are directly attached to the same carbon atom, and there are two carbon atoms. So according to that n+1 rule, 2 plus 1, so 3. So you will get, if two protons are directly attached, you will get the triplet. Here there are three protons are directly attached to the carbon atom, same carbon atom. So according to the n+1 rule, you will get the quadret. So this off resonance decoupling gives this idea also. So whatever information was removed by 13C1H NMR decoupling, that was the regained by the off resonance decoupling method. Here one more thing is very important, that it is the two bond coupling is not observed by off resonance decoupling. Two bond means this is the one bond, carbon carbon and carbon hydrogen. Okay, so C H, sorry, here it is the H. Okay, so this is the one bond, this is the two bonds. So you can say that two bond coupling is also not observed. So it is there when the spectra is taken, you will get it, but when off resonance decoupling is imparted, then that coupling can be removed. So whatever I have discussed, that is mentioned here in the simple way. Three protons are there, so it gives the methyl proton, so it gives the quadret. Two protons are there, so it gives the 2 plus 1, 3, so it is a triplet. One proton is there, so it is a methine proton gives the doublet, where 0 proton is there, quaternary. Okay, quaternary carbon is there, so it gives only one peak. So in nutshell, you can say that 13C NMR spectrum of compound can be run twice, so that all the information can be regained. So it gives an idea about the singlet in the BBD proton decoupled spectrum, number of non-equivalent carbon atoms, and then their chemical shift. The multiplicity of the peaks can be observed by the off resonance. Okay, see the difference. Once another example is, this is the decoupled, you can say it is the BBD, and here it is the off resonance decoupled. So here you can just see that it is only singlet was observed, but here it was observed quadret. So that is of the methyl group. Okay, it is the same spectrum, by the way. It is a so three protons are there. Okay, three protons are there. So according to the rule, it should mention quadret, but here it was showing only singlet. It was showing only singlet in BBD, but that noise is removed. So now it is clearly mentioned quadret in the off resonance decoupled, and it must be the quadret because there are three protons. So 3 plus 1, it should be quadret. Okay, the another carbon is here, it is the CH2 somewhere here. Okay, CH2. So CH2, it is the C. So here also it is mentioning only singlet, but CH2 means it should mention the triplet. So here it is the triplet. Here it is also showing only single carbon atom, so it should be singlet. So here there is only one carbon atom, only one carbon atom is there, no attachment is there, so that is why it is showing the singlet. So this remains same, this remains same, but this is the difference that observed in the BBDN of resonance decoupling. So this formula is very important. This formula is very important. Without taking any spectra, you will able to calculate the carbon value of any of the carbon atom of any carbon. So for that you need to remember this formula. Delta I is equal to minus 2.6 plus 9.1 n alpha plus 9.4 n beta minus 2.5 n gamma plus 0.3 n delta. So you can able to calculate without any graph. You will get an idea about the carbon. Okay, now you can just, I am just showing here you, it is a CH3. So it is a toluene, you can say. Okay, now you can able to identify the value of this carbon atom. So when you wanted to identify the value of this carbon atom, so first you can number the carbon 1, 2, 3, 4, 5, 6 and 7. So you can say that there are total number of carbon atoms are 7. Okay, now you wanted to find out the value for carbon number 1. So here you wanted to, you can say delta 1. Now it is minus 2.6. So here it is the substituent. Okay, so you don't have any of the alpha or beta or gamma or delta carbon atom. So chart will be given to you where you will get directly value of the phenyl substituent. This is the substituent. Okay, so you can say this is the one of the substituents. So directly XYZ value will be given. The phenyl ring is attached. So let's say it is having the, I don't know exact value of this. We need to see the table, but I don't know. It is not there ready to use with me. But you can. It is possible to identify that. So you will be given value. So that probably it is a X. So delta 1 is equal to minus 2.6 plus X. X is suppose it is a 40 suppose. So 40 minus 2.6. So that will be the value of the delta 1. Now this is the another example I can take. CH2, CH3, sorry, CH2 and CH3. Okay, this is the one of the very simple example. Now you can number it 1, 2, 3, 4. Okay, 4 carbon atoms are there in this molecule. Now you wanted to find out the value for this carbon atom. So in the, according to the formula, what is the number of this carbon atom? 2. So you can mention delta 2. Okay, now minus 2.6 9.1 into n 9.1. So 9.1. Now how many alpha carbon atom is there? Alpha carbon atom. So this is the carbon. So you can neighboring one, it can be alpha. Sorry, this is the carbon atom. So it is not related to that that functional group is attached to the carbon, that can be considered as a alpha. That can be considered as a alpha. Okay, and beta, so beta dash, so 2, alpha is only 1, so plus 9.1 into 1, okay, plus 9.4. 9.4, how many beta are there? 2, 1 and 2, so 9.2 into 2, and there is a beta value, one value of beta will be given to you, so you can put that x, so that can be multiplied by this. Okay, so this is the 2, so 9.4 into 2, 9.1 into 1. Now how many gamma is there? So alpha, beta and gamma only one, so you can say that here minus 2.1. So now you can sum it, so you will get an idea about the each carbon atom. So this is very useful technique to calculate any of the carbon value by manually also. In Kalsi, the calculation is given. In Pavia, it is not mentioned, but in LDS Yadav, it is also mentioned. Okay, so you can refer it there, how to calculate that values. Okay, so tables are given. So we are not going to ask such kind of questions in the examination, because lot of values and table uh, must be given, but that table is take very more papers, so that is why we are not using that technique. But for your simplicity, you can remember this formula, how to calculate the carbon value manually. Okay, good. Now this is the modified method, that is the DEPT. It is known as DEPT, Tistoneless enhanced polarization transfer, and it is the heteroannular correlation spectroscopy. So coupling between the close lying proton, that is the homo nuclear correlation, and connected with the C and H, that is the heteronuclear correlation. So this gives an idea about this. In short, it is known as the DEPT. Okay. So DEPT is what? Distone-less enhancement by polarization transfer. So this is very useful technique by difficulty to identify the proton by BBD and off resonance decoupling. So this method can be help us. So you can, by the time you can go through this, I can have the water and then I will start within 2-3 minutes. Just we can start within 2 minutes. Okay, so once again, welcome. So DEPT is advanced method to identify the nature of the carbon atom. So it distinguishes between the primary, tertiary, primary, secondary, tertiary, and quaternary carbon atom. Because in BBD we had seen that lots of couplings are there between the carbon-carbon, between the carbon and hydrogen, between the first number carbon atom and third number carbon atom, between the first number of carbon atom and fourth number of carbon atom. So a lot of complexity is occurring. So in DEPT, with the help of this method DEPT, it clearly gives the idea about the nature of carbon atom. So for that, at different angle, the pulse can be measured. So in this 45-degree, 90-degree, and 135-degree, these three angles are taken to identify the nature of the carbon atom. So this slide will give you clear idea about how this worked out. Okay, so DEPT 45 DEPT 45 gives the spectra with positive CH, CH2 and CH3. All these signals with all protonated carbons, correct? Here we are not talking about the quaternary carbon because it cannot says it cannot observed by these techniques. It gives distinguish between this. Okay, so automatically when DEPT is not mentioning any of the carbon atom beyond this, then no such kind of carbon is present. Okay. So at this angle DEPT 45 angle, it gives all the three. So now with this we will come to know that there is no quaternary carbon is present in the particular molecule. Okay, so this information will be received by DEPT 45, correct? Now DEPT 90, so at 90 angle it yields only CH signals, CH carbon atom. So you will get an idea that how many carbon atoms are there, that is like a CH carbon atom, only one proton is attached. Okay, and DEPT 135 DEPT 135 spectra, that is the that gives the CH3. But here very important thing is that CH2 gives the opposite phase in the downward, so this will give you the positive signals, positive upward, whereas CH2 gives the downward. So you will come to know that the how many CH2 carbon atoms are present. Okay, so DEPT 135, DEPT 90, DEPT 45. So what is the difference between DEPT 135 and DEPT 45? In DE45, all the signals of CH, CH2, CH3 will receive, but that will only in the positive side. But in DEPT 135, only CH and CH3 will give in the positive side, and negative side it will give only CH2. So this type of signal will be received. So now this is the normal 13th spectra, where quaternary carbon, methyl carbon, and methyl carbon is given. Okay, but in DEPT 45 we had mentioned that all the positive value will be mentioned. Of course this is not considered in the DEPT. So DEPT 45, these are the positive value, but in DEPT 135 both are the positive value. Which one? The CH3 CH3 and CH, but this is the negative value, CH2, where in DEPT 90 only CH proton can be observed. So this is the whole idea about the DEPT. So this is the one of the example that is mentioned here, where the DEPT 135 is taken. So only you can see that if it is visible, you can see that here it is the downward two peaks are observed, and here it is the one peak is observed. Correct? So 3 CH2 are there, is it? So you can say this is the one of the CH2, this is the another CH2, this is the another CH2, and this is the one more CH2. Correct? But if you look at this, both the CH2 are overlapping, that is common. So now how many peaks you will able to observe? 1, 2, and 3. So these 3 CH2 peaks are there. Correct? Now this is the sp3 hybridized. Okay, all these are the sp3 hybridized, but this is CH2 double bond something. So it is the sp2 hybridized. So that is why it is towards the downfield. Correct? Because this carbon, are you able to see this carbon? I am rounding this. Okay, this carbon atom CH2. So that is the sp2 hybridized. That is why it goes towards the downfield. Rest is the towards the upfield, and rest is the different carbon atoms here mentioned. This is the CH3. Okay, terminal CH3. Here the CH3 is CH. Here is also another CH3. So you will get such kind of spectra by the using of the DEPT. Okay. So this is the toluene. Already we have said that it is the same peak. Here it is the same peak. This is the toluene, same peak. So that is why this is the 1H NMR spectra. So range is from 0 to 10 is mentioned. It should be up to 12, but not an issue. So here you will get the highest peak is of the proton, that is the CH3, and it is the singlet because it does not have any neighboring proton. So it is a singlet HA. Okay. Now here you are getting the multiplates. In benzene, it gives the multiplates because the number of protons. So here 1, 2, 3, 4, and 5 protons are there. Out of that, these 2 protons are same. These 2 protons are same. This is the difference. So that is why it looks like a triplet, but it is a multiplet. Okay, between the 7 and 8. Now this is the carbon. Okay, this is the carbon. So you can see that this is the quaternary carbon. This is the secondary carbon, secondary carbon, secondary carbon, secondary carbon, secondary. This is the tertiary carbon, and rest is the CH3. So this is the CH3. Okay, now we are having the different carbon. So this is the CH, 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 CH. So this is the CH. Okay, the value has more or less vary due to the substituent, but 3 can be observed. 1, this 2 carbon will give 1 peak, this 2 carbon will the another peak, and this para carbon will give the another peak. So that is why all these are the 3 peaks. The value are the difference in value is very less, and this carbon is the single carbon, that is the quaternary. Tertiary it is. This is so it is around the 139. Now ketone is very easily distinguished. So that is why already we had mentioned the different values of the chemical shift of the carbonyl carbon. So ketone is having highest 2005 to 220, then the aldehyde, then the carboxylic acid, then the amide, anhydride, and the ester. So this is the values. This is just for your knowledge and information how this impacts. You can able to calculate the carbon value of each carbon by using the delta I formula. Okay, so this is the 13. Then now there are two substituents, so this carbon value is 28. Now this is the sp2 hybridized carbon atom, so values are high. Okay. Now here just I wanted to mention that this value is 66 because the carbon is attached to oxygen atom, so this is also having same, so it is having only one value. Okay, uh, where I this we can see. Okay, here it is. So highest value, this is the ketone, so 209. Okay, because or oxygen is attached with the carbon atom, so it will go towards the downfield in the graph, so it is having the 209.7 carbon value. Now this is the neighboring carbon atom. Okay, so it is having 41.9, but this is away from the carbonyl group, this carbon atom meta, so it is 26.6. And para is more away from this, so that is why it is 24.6. Okay, so that's how it goes. This is the some molecules that is given and different values are given. You will able to calculate by using that formula also. Now the new spectroscopy, new technique is involved, because in 2D NMR, 2D NMR correlation peaks are used to help the establish the structure. Okay, so in 2D NMR we will get the 1x, I mean two dimensional, so x and y. In 1D you will get only the single peak that so far we had seen. Okay, but in 2D NMR, x-axis and y-axis both are utilized. Okay, both are utilized. So this will give you the more idea about the coupling pattern, whether carbon carbon is coupled, carbon hydrogen is coupled, or carbon and the neighboring delta carbon is coupled. So that can be considered in the 2D NMR, 2D 13C NMR. So COSY, that is the correlation spectroscopy, and NOSY, that is the species nuclear uh, heteromolecular spectroscopy. NOSY and COSY are there, but NOSY is related to space. When stereochemistry is involved, then NOSY is very useful. When stereochemistry is not involved, then COSY is useful. So you will come to know by looking this. So here it is. So, now NOSY and COSY are both common for the 1H NMR and 13C. Okay, so in 1H NMR, it directly gives the proton idea about the proton. So in 1H NMR, this is the 1H NMR. So just I can see that what will be observed by this, you will get the doublet. Here you will get doublet. Why do you get doublet? Because neighboring is having only one proton, so 1 plus 1 2, so you will observe by doublet. What do you observe by this proton in 1H NMR? What do you observe here? Sorry. Again it is hanged, so just I am restarting it. You can hold on for a minute because it is not responding. My laptop is not responding. Just I am restarting it. Okay, I'm back now. Okay, fine. So I was is it not showing? Okay. Yes. So here I wanted to slide is not changing. Wait a minute. Stop sharing. Mm. Are you able to see another slide apart from
No, sir.
not yet? EQF, COSI, something like that. HMQC. Are you able to see?
No, sir.
Okay, okay. Just, now you are getting. Okay, are you able to see BBD slide?
No, sir.
No, sir.
Okay. It's a very slow responding it is. Hello? Hello. Yes, are you able to see the two-dimensional NMR spectroscopy includes slide?
No, sir.
Which
No,
slide
sir.
is which slide is visible?
First,
Good
good morning,
morning, sir.
friends and
The first slide. Array. Okay, so I think some technical glitch is there. So I will continue the rest of the 13C. That is the advanced spectroscopy in 13C later on. So you can get in touch with the group details. So I will let you know today or tomorrow. I will continue. Okay. So thank you so much and do well. Okay, so now we are completing this lecture and then we will proceed in the evening or tomorrow. Okay, now you can leave the meeting, not an issue.
Okay, thank you, sir.
Welcome, welcome.